Good afternoon, ladies and gentlemen. Any ladies? Yeah, some. Right, before we begin, thank you very much for showing up. The presentation that we're going to talk about today is Cisco shellcodes, obviously, and a bit about backdoors as well. I'm Gyan Chaudhary, Senior Security Consultant from IRM, and Varun?
I'm Varun Uppal, Senior Security Consultant at IRM as well. IRM is a firm based out in the UK, so that's where we flew down from.
Yeah, just before I say anything, as you might have already noticed, I have a bit of an Indian accent, and I do sound like Apu from Simpsons. So if you guys have any problem, just note it down and we can talk about it later on. Right, so the agenda for today is just a bit of the background about iOS, how we started it off, why we did it. We'll go through an example of how to debug iOS, because that's the main challenge in order to make a working shellcode for iOS. Some of the tools that we developed, this is things like scripts that we wrote for automation of finding functions and converting some addresses and shellcode, things like that.
Exactly, some open source utilities as well.
Yeah, then obviously the shellcode itself. We also want to talk about the Checkkeeps issue, because this is something, it's a key to exploiting iOS bugs, and also in the case of shellcode, before we actually run a shellcode on iOS, you need to fix up a few things in order for it to run successfully. And we'll cover it by the impact scenarios and also the conclusion, the mitigations, how we go about it. So
the only thing we won't be talking about is probably exploitation of the Cisco iOS. We won't be really covering anything like uncontrolled pointer exchange or anything like that.
Yeah.
So it's mainly going to be the shellcode and the backdoors. That's about it.
Yeah. So, firstly, the whole research concept of iOS started off back in 2005. Michael Lin and Black Hat had already spoken about this stuff, but unfortunately, for whatever reasons, most of it wasn't covered and wasn't, people didn't know about how it works and what exactly goes behind and why should one create an iOS shellcode. So that was one reason. And secondly, we work for a lot of financial institutions, and there was some requirement for us to do this research. That's how we started off with this whole thing back in 2005. And also another reason is that, mostly like other conventional operating systems like Unix or Windows, very, very less has been done on iOS security. Yes, you do have a lot of papers coming out on FRAC and things like that, but eventually, what Michael Lin did was something totally, groundbreaking. The fact that you could reliably exploit a buffer overflow, which so far, has never been done. And even if it has, it is quite, in a very lab-like environment. So from that point of view, also, we want to take a look at it. Also, the thing is that, like, a lot of people think that iOS security or making iOS shellcode is quite a difficult thing. Web Security Focus, I think in 2005 had, released a paper saying that it might take easily up to 6 months for someone to start from scratch. It didn't take us even less than 3 weeks to come up with this without having much prior experience in active buffer overflow exploitation or, memory corruption exploits. It's much easier than writing an exploit for Linux or Windows, to be honest. And we'll show you that in the presentation. And
and the other thing is that if you look at it, the way things are going for operating systems like Windows and, for example, like software like Adobe and Java by Sun Microsystems, they automatically push updates as soon as they uncover any vulnerability, and, they push out updates and patches automatically. So I'm not sure about that, but I don't think that automatically happens with Cisco. It does happen a lot of systems, and people have been targeted follow that practice. So it's more of a manual and base process of actually getting it firmware and then putting it on the user interface. So it all depends on how aware a sysadmin actually is of a vulnerability coming out and then patching it. So the time difference or the lag between a patch being applied manually and the vulnerability being discovered is actually quite significant. And that always gives a attacker the opportunity of, capitalizing on it. If left unpatched for a couple of weeks or whatever. So that's why we believe that iOS is actually quite a lucrative target and something that needs to be investigated further.
Yeah, and also like we mentioned, most of the mitigating factors for iOS have been just updating your firmware, and obviously that isn't, it's not, there's no silver bullet for actually, you can't just upload, you just can't go to an administrator saying that, go ahead, upload your image. So there has to be some way, in order to have any countermeasures from these sort of attacks. So, right, a quick introduction about iOS architecture. I'm not going to go too much into detail. You don't need to actually. This is more from an exploration point of view, while we are talking just about shellcodes. But anyways, it's monolithic in architecture. What that means is everything is wrapped up into one big flat file, an ELF file, and everything is integrated. It's not a modular operating system. Yes, you do have, higher end routers like, I think it's 12,000 series GSR routers. They have a QNX-based modular operating system, but at least for the low-end ones, it's still a monolithic architecture. What makes that interesting is that there's no virtual memory protection mechanism. All processes are completely open, and if you can sabotage or overwrite an address or overflow a buffer in one process, you can easily break out and play with some other process's memory, and that's what makes it much more interesting and much more easier to exploit compared to a traditional operating system with a fully implemented virtual memory space. And it does use stack and heap space data structures for managing stuff, but again, even the stack data itself is stored in heap, so even if you do find a stack overflow, it's pretty much straightforward exploited, like a heap overflow. Right, we'll start off with iOS debugging. Like I said, this is the most important part about iOS exploitation, because if you get this correct, everything else is pretty much straightforward. The lack of tools and software applications for debugging iOS is what makes it so difficult. And once you have this outside, it's pretty much straightforward, just like exploiting any other operating system. So the image itself is compressed in a zip file. It's a pkzip format, slightly modified by Cisco. When you actually load a router, there's the bootstrap itself will unzip this image and load it in the memory. When in our case, because you want to reverse engineer the image, we need to extract the original iOS file. So you just run an unzip command on it and it'll pretty much do the job. You can use WinRAR, stuff it. That's what Michael Lin used, so that's why we copied from there and we used that application, and it worked pretty well. There's a slight, the guys at Cisco have changed a few bits and bobs for, making it a bit difficult to exploit, or rather load the image in IDA Pro. Again, the way it sounds, when a lot of people say you have to fix the ELF header and you have to make a lot of changes, it's not at all like that. It's just one simple change in the ELF image and you're all set to upload it, load it in the debugger. So what you do is, there's one flag which is the eMachine header. This in the ELF header itself is changed to, I think, Sun Spark. So when you load it in IDA Pro, it starts translating it into the Spark architecture, and that's a bit of a problem because we are working on PowerPC. So obviously, you just change that bit, save the file. You can use a hex editor and save this bit. And you just change it to OX14, and then you have, when you load in IDA Pro, it will automatically recognize, and that's it. There is no sort of black art to it. It's just that straightforward, and you can load it in IDA Pro. Secondly, this is more from the actual shellcode development. The reason we decided to go ahead with creating shellcodes for iOS. So one of the reasons was that we didn't have a vector to test our shellcodes in the form of an exploit, and that would make it very unreliable. We were really focused on just seeing how Michael Lin created these shellcodes. That's what the goal was. So we didn't exactly use it in any active payload in the form of a buffer overflow exploit. For that, what we did was to emulate a vector. We used GDB itself, and GDB has write commands with which you can write in the memory of iOS itself. And so we emulated a buffer overflow by actually overwriting certain parts of memory with our shellcode and then directly jumping to it so that we can execute it. So for that, we needed a fully working GDB debugger which could talk to the remote router. Again, there are some articles on the internet about how you go about debugging GDB with using serial line. Quite an old article, and Cisco, since I think GDB has since 6.0, completely stopped supporting iOS. So we had to modify GDB ourselves. Also, there's the issue is that when you attach, I'll just go next slide actually. Yeah, I think yeah. The way GDB actually works is it has a serial protocol which encodes your requests and it makes it in a format which Cisco can understand, the Cisco GDB stub, and that is slightly broken. And what will happen with that is because we are trying to set, using the set command in iOS, we are going to be writing a shellcode in memory. So what happens is that because GDB is slightly broken, the minute we actually upload a shellcode, it gets modified into a different format, and even though it's correct, it won't get executed. So you have to modify it in a certain way so that you can clearly talk with the router. So we'll just show that. First of all, you have to edit the configuration file in GDB and create a new target for Cisco, because that doesn't exist anymore. So in this case, if you see the first bit of it, we remove that and we just add another version with Cisco Core Big VEI IEEE whatever. We didn't know what that is. We just simply pasted it so that we get a vector for compiling. Then there's a file called remote.c, which is actually responsible for sending serial data, and it has two modes. There are two modes by which it works. The first mode is the classic GDB way of talking to using the over serial, and there's another mode which Cisco uses. So basically, whenever you attach a GDB session or a GDB debugger to Cisco on the iOS, it will by default fall on this mode. And the problem with this mode is that when you attach it, it will start misaligning memory addresses and you can't see anything, which makes it quite difficult. So all you need to do is remove this line or this variable which says remote Cisco mode is equal to 1, and you compile it then, and you have a fully functional debugger. Again, there is no rocket science. There's nothing complicated about this. All over you see a lot of email lists and everywhere where there are a lot of people are pitching ideas and tools that you can use to debug iOS, and you don't need all that. You just modify this much and you've got a fully functional debugging environment. Again, something so straightforward and scale at the same time. So.
Do you want to just talk about the?
Yeah, this is just an example of once you've patched it, you get an option for PowerPC, and then you just attach. As you see, you can just attach it to the serial line, and that's disassembling the main data segment. Now, one thing interesting to note is that Cisco have by default disabled some of the commands which were earlier used for looking at router memory, and this way you can bypass that protection. So you don't have those memory commands anymore to protect. They have basically removed the command itself. But in this case, what is the show memory? Yeah, it's the show memory command, and it doesn't work anymore. So this is a good way of although they have disabled, you can still look at the memory using this command. If you see, it shows pure PowerPC instructions, but if you did not compile with that patch, what would happen is it will just come in a very different format. It will come in something like not sun, some obscure output. So, right. Yeah, there's one limitation, although, we can attach the router with GDB, and we can write our own addresses in memory with our shellcode and things like that to test it out. But however, you can't step, or you can't continue, or you can't do next. You can just put one breakpoint, and you can just, after one breakpoint hits, you cannot again attach or break another, put another breakpoint. So every time you start off while reversing when you're reversing the iOS, you just have one shot, and after that you have to again start the whole cycle. So if anyone out there, who is interested in this, just be prepared to reload the router around 100 times or something. So yeah, we did it. We had time on us. So, right, the way we write our shellcode is basically in pure PowerPC assembly. We used the GDB cross-compiler and GCC bin utilities for PowerPC. So we got that working, and We assemble it using the gas assembler, and then again, it's pretty much straightforward, just like Linux. You extract the opcodes using objdump. Now, one thing that there's a problem is that, because the output of the opcodes is pretty much big, and you need to use a set command. So, set the address where you want to write your shellcode and the shellcode itself. Now, this has to be generated in multiple set commands so that once you attach to the debugger, you can, directly set your shellcode in memory. So to do that, what we did was we just wrote a small shell script which will take this objdump output and, basically convert it into a GDB file for you, which has all the set commands. So you just put that in the debugger, and you can, directly write your shellcode in memory, in the runtime iOS memory. So what we do is also, because we're trying to emulate a buffer overflow, what we do is we take a certain part of memory or a function which is called by iOS every 30 to 60 seconds or whatever, and it directly jumps to our shellcode. So what we decided was because Checkkeeps is a process that starts every 30 to 60 seconds, we just thought, might as well patch that piece of code and then just wait for it to trigger so that we can execute a shellcode. So we use a GDB init file for that. So if you can see, the first command is the remote serial line that's we attach to the GDB. The second bit is the actual code that we use to jump to our shellcode, and then there's a return function where once the shellcode has done executing, it will jump back to this return, and it will start working normally again. The router won't crash. And what you see, the source shellcode.txt is actually the shellcode itself, which will be passed to the router, which will override the memory. That's just a screenshot of what the script looks like, pretty dumb. But yeah, this is how it works. It generates a set command with what to write and where to write the address at. And this will be automatically done in the runtime memory where we are trying to emulate our exploit. Alright, this is just a sample hello world for Cisco, which we'll go through step by step in the next presentation. It just takes a string, and if you can find the printf equivalent of iOS is what we use, and then we just call it. I'll go through the whole detail of how we do that. Basically, in our case, we are going to be invoking software APIs within iOS, which will do all the job for us. It's just like Unix or Windows, where you call different functions to achieve your end result, which is a shell. So in this case, we use the mtctr and bctrl instructions, and it's basically if you make a small C program and if you use the attribute long call, and if you just look at the assembler output, this is how it looks. It uses the mtctr btctr pair, and what that will do is once you have loaded your address of your API that you want to call, you just give it the mtctr call. What that will do is it will load the function address in the count register, and then the branch instruction will automatically go to that piece of code. That's how basically you would invoke a function in iOS. That's just a sample code of how it's done. So you break the address typically and into high addressing and low addressing, and you load it in any register you want, and then you just call this pair of functions, and you can call all sorts of function calls. Right. So we reversing the iOS. I mean, like I said, you fix the image, you uncompress it, and the biggest problem is that most of these images are quite big, so they do take a lot of time, being loaded in the debugger in IDEA Pro. So what we did was we just used a smaller version of the iOS image, which was 2 MB. It was for iOS 11, and that loads up pretty fast. And if you look at most of the images, although there's a lot of different changes, essentially the main iOS subsystem, the kernel, the timers, everything is at nearly or more or less on the same addresses, and that's it's simply, if you just use any other old version, also it will do. So you can use that. And also, what we did was most of the functions that are stored in iOS, the relevant strings or functions and arguments, everything is stored just above the function itself. So that way you can easily, things like, say you want to find a function for Checkkeeps. If you want to know where Checkkeeps is in memory, what you do is you issue the reload command, and the reload command will, or just crash the router using any sort of, you can use any denial of service exploit or something and crash the router, and all the strings that you see, you log those strings, and then you can directly search them in IDA Pro, and automatically just above that string will point to the function, and that's your main function for Checkkeeps or for reload or for crashing or for anything. So that's how we use it to actually identify functions. Just to give an example, I mean, this is something that the approach that we used for connect back shellcode. We saw that if you enable the finger daemon on iOS, and if you run finger against the router, it will show you the output, which is exactly the same output for show users command if you log in locally to the system. And what we did was we looked at some of the strings we captured the strings and we tried to search in the main IDA output, and you saw that there are a lot of functions, interesting functions that actually ran the command that you used. And obviously, if you're going to, by using finger, if you can run the command remotely, so there is some sort of interaction happening at a network level. So we knew more or less that's how we localized the functions that we wanted to see and use for shellcode. And again, we just logged the output and went from there on. There are some other functions that you can use. There's the show memory, show context, reload. This is the function that we used for actually finding Checkkeeps, which I'll talk about later. Right, Varun, you can take on words from.
Okay, starting here with the actual shellcode development process. So what we had was we were intending to create two shellcodes. One was supposed to be the bind shell, and the other one obviously reverse shell. So I was working with the bind shell stuff, and while Gyan was working with the reverse shell. The first thing that came out was actually the bind shell. When I started working with the bind shell, I thought to myself that there must be a different way of doing this bind shell apart from doing it the standard way like you would do on, say, a Windows operating system, or say perhaps.
Speak a little.
Yeah, sure. So I thought to myself that there might actually be a better way of doing it or alternative way of doing it than rather just trying to locate functions like, say, bind and listen, and the standard way you would do it on a Windows or a Linux operating system. So. Coming from a penetration testing background, I did come across a lot of routers in the production environment, and the way a lot of people would actually stop access to the routers would be, or prevent telnet access to the routers would be issuing things like, say, going to config mode, going to line vdevice 0 to 4 and say transport input none, or just disable the first 5 vdevice lines that are enabled by default. So what we did was we thought to ourselves that, is it possible to actually, let's say, if you have physical access to the router and that you want to actually, enable a new VDY line, you want to start off a new VDY line, and let's say how would you actually go about creating a bind shell if you actually had physical access to the router? So what we did was we came up with a concept that we took a router, we disabled the first 4 VDY lines, and then identified 4 functions that would actually help us go about building this shellcode. Now, the first thing that we did was we created a new VDY line. So the first 5 VDY lines have been disabled. So what we did was we spawned a 6th VDY line that would automatically enable telnet access to the router. So let's say if in a production you have a router that has absolutely no telnet access whatsoever, you run the exploit with a payload that would allow you with a bind shell payload. So the first thing that's going to happen is actually it's going to enable telnet on the router, and you'll be able to telnet. But because it's a new VDY line, by default, it's not going to have any password associated with it. And because it doesn't have any password, it's going to say, password not set on the line. And for that, what we had to do was, the second thing we did was, you have to actually set a password for that VDY line before you do anything. So in order to set a password for the VDY line, before you do that, I'll just move on to the next slide, so let's assume that you're actually working physically on a router. So for every single command that you issue on a router, there is a structure in memory that gets populated. So let's say if you want to set a password for a line, so you would go config mode, line vdevice 04 or line vdevice 5, whatever, and then you would issue the command set password. Now, before you issue that command set password, you actually need to populate certain sections of memory or the structure that existed in memory. What it does is, right there. So what you do is, whatever line that you want to set the password on, at that particular offset in memory, and these offsets are just particular to the iOS image that we were working with, you need to tell it the VTY line for which you need to set the password. And then there's that's what we call it, change pass. You invoke the change pass function, which is done by like Gan mentioned early on, by loading the count register and then jumping change pass. And at the same time, you include the address for the command information structure, that structure in memory which says for which VTY lines you actually want to change the password. And once you've done that, it's like a two-stage process. The first stage is like you made the new VTY line. Second stage, you gave it a password. So before you give the password, you actually set up the whole structure in memory. And once you've done the two things, once you try connecting to it, you're going to get a user access verification prompt. And you enter the password that you supplied as a part of your shellcode, and you get logged in. So, but what you want is level 15 access, isn't that?
Yeah, that's true.
Yeah. So now the second thing was to actually escalate privileges. So the third thing is to escalate privileges. So what we realized was that what we actually identified was that for every single VTY line that is running on the router, there is a structure associated with that VTY line. And that VTY line in that structure is a parameter that actually has, or is a field value that actually has the code or the value for that defines what privilege that VTY line actually has. So what we did is, for every single VTY line, there actually exists an array. There's an array in memory that actually points to each and every single VTY line. So what you do is, from that array, you identify the new VTY line that you created, the new VTY line on which you set the password, and at that particular offset, you just set that particular value that says it's supposed to be running at level 15. So this was all done, while issuing commands to the router and setting breakpoints correspondingly, observing, what sections of memory have which parameter value or which function was being called with which parameter value. So essentially what happens is, let's say if you have a fully functional bind shell and you put it as a part of a payload, run it against a router, the first thing that happens is it'll create a new VTY line. Your shellcode is going to have the password that you want to supply. It's going to give it a new password for that VTY line, and then you can telnet into it. As soon as you telnet into it, it's going to give you a user access verification prompt, and once you enter your password, you get dropped immediately into a level 15 access. So that's how the whole bind shell thing went about. So what we've done is we just use all functionality that was there in the router. Nothing new. We didn't even bother finding out bind or listen or any of those functions. So literally, whatever actions like a sysadmin would do on a router, we just translated that into or we just gave it a programmatic way of doing it. We have a video of that. You want to just quickly? Yeah.
What's a W? No.
Let's play it in media player.
It's old school.
No. Okay, so what you can see now here is it visible?
Yeah.
Not there.
Can you see it on?
Just one second. Guys, can you see that? I don't think so. It's just coming out blank, isn't it? That is kind of weird.
Yeah, we'll just upload it on the website or something later on.
It's not on the CD, but we could. So I'm going to translate what the video is actually doing. So what we've done is we've got two windows open on here, and in one of the windows we're configuring a router like it would be put into a production environment, no telnet access whatsoever. And then what we do is we log in using GDB, and we take the shellcode and upload the shellcode, paste the shellcode in the Checkkeeps section of the memory, and Checkkeeps is probably going to run after like.
Okay, it's Microsoft DRM action. Yeah, it's because it's made in a different format.
Oh, I see. So yeah, so in Checkkeeps is probably going to run after every 30 seconds or something, and when that runs, when that function gets called, because our shellcode has been plugged into that part, it gets called automatically, and the shellcode actually runs. So what happens is we've tried to show that someone's trying to telnet in the router, there's nothing accessible, and once the shellcode runs, you can telnet in the router, enter your password, and you log in as level 15. So I'm just a bit sad that the video is not working and can't see it, but the video is actually on our website as well, but try to figure that out.
Yeah, we'll just figure it out.
So once the buy-in shell was done, like I mentioned, there were 4 main functions that we had to identify, like something that helped us create a VDY line, and that took in just one number. That's about it. Then we needed something that helped us to set a password, change password on the VDY line, and obviously the other addresses were the addresses for escalating privileges for that VDY line. The second shellcode that we came up with was the reverse shell that Gan was working on.
Yeah, I'll just... Right. Basically, reverse shell, you would again assume that you need a TCP connection which will go outgoing on the attacking side, and you just have to bind a shell to it. In the case of Cisco, there's a very interesting function that can be called which will do all this for you. And again, we found it using the finger command. What it does is, first of all, you need to create a VDY, and you again elevate it to privilege level 15 because that's the shell that you want. And you open a TCP connection and you associate the VDY with that TCP connection. So, it's again very straightforward. The function that I'm talking about, we've called it execute command. What it does is it takes the command name and it associates that command name with the TCP structure, so that, say for example, in Finger you would use show users, and the output will be redirected on this TCP structure back to on the remote side. What we did was, this is how we made the shellcode. We used one of the functions, which is actually a function which will open a connection outbound, and it takes a local port, local IP, remote port, remote IP argument with the VDY structure that you've created, and it would run the command that we had given it. But we wanted a fully interactive shell rather than something that just executes commands for us. So what we did was that this function, this execute command function, it takes a string value of the command itself. What we did was we just passed a null as an argument to this function, and what that did was it just gave us a fully interactive reverse shell. So in all, you just need, technically speaking, you just need 2 functions, which makes this shellcode quite portable. And that's how we used it to create the reverse shell. Again, I don't think we can show the video. It's just a netcat listener, and you just wait for the connection to come back. Right. The most interesting one, I think, from our perspective, was this 2-byte shell. This is, in fact, you don't even need a reverse shell or bind shell. This one is, you literally have to manipulate 2 addresses in the memory, and you have a listening shell on a router. And based on what Varun had done with the bind shell, we identified a structure in memory which stores all this information about each console. And there was 2 locations in memory in the structure. If you override them with a positive value, you don't even need any other, you don't need to set away anything else. If you just add a positive value to it, you automatically get a low privilege shell. And if you change that with a OXFF, that's the bit is switched on, and you automatically, the shell becomes a privilege admin level shell. So just these 2 addresses have to be overwritten, and you don't need a fully working shell code as such. I don't think we have a presentation for that again. Yeah, this is just us. We wanted to go through all the 3 shell codes, but we thought that would be an overkill. We just thought that we'll show you one of the sources for the shell code. We are releasing all of them on our website pretty soon. That will be the reverse shell and the bind shell also. So this is just a quick example of how the 2-byte shellcode works. Not when I say 2-byte, I don't mean the size of the code itself. So basically, you load the login structure is stored in memory at that address, and you load that structure, and you patch that address and location with the privilege, which is you load the privilege level first, and then the address where the actual privilege structure is stored, where you have this bit of information which controls your authentication level, and you change that with that value, which is OXFF1. And what that will do is it will patch the runtime router with that value, and it will automatically escalate the privileges for you. And then all you need to do is just return, and you can just tell it to the router. So if the telnet has been disabled on the router completely using the line BTY no something, if you transport input none, you still can bypass that with this technique. And again, I mean, as we talk further, you can literally make on-the-fly backdoors and routers without having to actually use an exploit or anything. I mean, these codes don't just act like a shell code. They can also be used as memory resident backdoors if you can physically compromise or attack a router. So, yeah. Like I said, most of these techniques have been, what we saw was, I mean, although we started off as just using this in a vector, which we did later on, we found that, they definitely can become very stable backdoors in memory, and, without crashing the router itself. And you can literally you can bind ports on a router, you can add new functions, you can make lines which can listen on high ports. You can do all sorts of fancy stuff. I mean, and also what you can do is that you can, if you want this, obviously if the administrator decides to reboot the router, the stuff will go away. So you can, I think Core did a very good presentation in CanSec West about using these backdoors, by literally manipulating the image and repackaging it, changing the checksum value and things like that. But what we did was, I mean, the same stuff with these codes can be achieved. And you can, make certain trigger patches which will wait for an ICMP or things like that, and or a packet, and it'll automatically execute the shell. So you can use them as backdoors also. We wrote a small application, in fact, which would basically utilize a for loop and scan IP. If given an IP address, it will automatically scan within the internal network for an IP address. We'll be releasing that code as well. Again, it just uses simply the connect function in Cisco to, just fire out connections for certain ports, and it will print them out back to you. So that was quite interesting.
Exactly. It's like, using the same techniques that we use for bind shell, you could possibly use that same technique again. You can fire it off as a payload, and let's say there are 4 VDY lines that are enabled. You could have like a 6th VDY line that's open, and because the sysadmin doesn't actually know about it, so if you connect to the 6th VDY line, you get presented with a level 15 access straight off.
Yeah, so again, I mean, if you run a show config, there'll be no changes in the configuration itself because you're directly playing with the memory within iOS. We thought that we'll talk about the Checkkeeps issue because this is something that a lot of people don't know about, and again, this is very much required for if anyone seriously does want to use. I mean, honestly, we don't feel that you'll see a lot of shellcodes and such vectors being used externally from the internet. It's just not going to happen. It's technically very difficult to make a fully functional exploit which will attack a router remotely from the internet and run these payloads. That's asking for too much. There's too much of static memory addresses that you need to know. You cannot exactly reliably fingerprint the iOS image, and even though you can automate the process of maybe finding functions in the runtime memory, it's not that straightforward. And it will, internally, yes, you can definitely exploit or use these payloads to create an exploit, because internally you can still fingerprint information and there are some more services open, but externally that's not possible. So again, the Checkkeeps technique that was very briefly covered by Michael Lin, this is something that we are interested in, how it works. So Checkkeeps is a process that is used for looking at any corrupted memory in iOS. Being an embedded operating system, you have to, at least there has to be some process, a minimal process, which will at least do a bit of housekeeping, look for functions, look for corrupted memory, and based on what it finds, it will, in this case, it chooses to reload it. Obviously, it will log a bit of information about the event before it actually crashes. So that's what the process does, and this is exactly what made it difficult, because every buffer overflow, more or less, most of the buffer overflows in iOS happen in heap memory, and the minute you corrupt any linked list or pointers, Checkkeeps will detect it and just reload the router. So there has to be a way to bypass this protection in order for you to reliably execute a shellcode. So before we go into that, what happens is the process Watchdog, there's a process in iOS which will, based on what the privilege of the process is, it will kill that process. And there's a very good book on iOS internals made by Cisco Press that talks about it more in detail, but we just given this slide here for understanding this Checkkeeps issue. So what it'll do is it will see that if when the scheduler allocates a process, it gives it a certain time to run. If it sees that the process has run beyond that time limit, it will issue a warning, and in the second case, it will immediately kill the process. And iOS processes are, they're allocated, their privilege levels are allocated by their importance. And in this case, you have 4 levels, and Checkkeeps is the lowest level, marked at, I think, 3 or 4 in memory. And again, because it's a low-level process, when the Watchdog timer sees that, Checkkeeps has run beyond a certain time, it will instantly kill the process for you. So what we thought was, there's also about iOS timers. The reason why I'm talking about this is because based on our research that we did for iOS, we assume, we are doing a lot of work on the ICMP v6 overflow that was also presumably used by Michael Lynn for this exploit, and we saw that he had used a timer linked list. So what happens is that if you try to use that exploit, if you run it against a router, what will happen is before the router actually crashes, you get a lot of timer linked list errors, and we assume that this is what he used. He used this linked list of the timers to overwrite the memory addresses, and this is just an example of Checkkeeps. When it sees that it's crashing, it will initiate a reload sequence, and before it actually reloads the router, it will to log in all the error messages and things like that. It will look for it will see if the process itself has been called by another process. This is to do segregation so that it can look at the errors, and if 2 functions simultaneously call the Checkkeeps function, it won't let that happen. So to do that, it does a check to see if Checkkeeps has actually been called by another process, and this is stored in a variable in memory, which decides, it's a Boolean variable, which decides whether to continue with the reload or to just simply return. So in our case, we saw that, if you override this address with any positive value, you can stop Checkkeeps from crashing the router. And this was again demonstrated by Lynn, and he used the timer linked list this is again, we've not cross-checked it with him, but this is what we think, this is how it was done. And this is, oh shit, we got the wrong presentation. No, it's this timer issue has been fixed by Cisco completely, and I think as far as the linked list issue goes, this bug still exists, but it's very difficult to exploit it. And the reason being that the vectors to actually override this address are totally based on the exploit environment. So yes, the Checkkeeps issue is still it's still open to exploitation, but it's extremely vulnerability dependent. You can't just simply override this variable directly. You do need you need to be very lucky, in fact, to get a exploit condition where you can play with it to this degree. So I think that much is it has been fixed to a high level.
It's just simply the way the iOS works. Checkkeeps works the way it's supposed to be working. Obviously there's going to be a Watchdog process monitoring and things like that. So Checkkeeps as such does not need any resolution. It's more about I mean, if you start resolving Checkkeeps, you might as well change the whole iOS architecture. But
again, because it's an open memory architecture, it's not, there's no one-time fix to it. You can still play with memory addresses, and in the end of the day, it's just simply based on the bug that you're exploiting. So, yeah, I mean, like I said before, it is quite straightforward, and once we release the shellcodes and the automation, we have written some IDA Pro scripts which can help you find these functions, to create a payload. And the thing is, a lot of, at least from what we gathered, people did mention a lot about the fact that it's quite difficult being a closed source environment. It is not that straightforward to create a shellcode, but that's not the case. It can be done and can be automated pretty much easily. And, you can make further stable resident memory backdoors and things like that. Honestly speaking, there isn't much, at this point of time. Yes, you can upload the firmware and things like that, and you can close all the unwanted ports and blah, 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 but it still depends, you need to be pretty proactive about it, because we feel, like I said, exploiting these issues externally is not possible, but from an internal point of view, the threat, definitely with this research and with the stuff that, Core has done before and whatever has come out, this is what we feel, that definitely this stuff is going to be coming out, and, you'll see more and more people using this sort of stuff proactively right from supply chain attacks, where you repackage images and upload them into routers and, do all sorts of things. So there will be a lot to see in this space, I guess. Yeah, that's about it. Questions?
Yeah, pretty much it.